तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we were discussing about effluent disposal. We have seen that the treatment plants can remove a certain amount of the pollutant present in the wastewater. Okay, we designed the treatment plant in such a way that what is the maximum extent possible, it will be removed in the treatment plants. But 100% efficiency is impossible in any of the treatment plants. So, definitely some amount of the pollutant will be left over in the effluent whatever is coming out of the treatment plant. So, what we will do with this effluent? This effluent has to be discharged in somewhere. Most of the time we discharge this treated effluents in existing water bodies or inland. So, what is the principle behind this effluent disposal is the treatment whatever is taken care by the treatment plant is okay, and whatever is left over the nature will be taking care and it will be completing the treatment process. So, when we discharge this effluent to existing water bodies, what are the important factors we have to consider? Okay, we should be aware of the self cleansing capacity or the carrying capacity of the stream, because what will happen, the stream it is having high dissolved oxygen and it will be having large volume of good quality water flowing through that one. So, when we discharge the effluent to the stream, what will happen, the organic matter whatever is present in the effluent, it will be undergoing biodegradation in presence of microorganism and it will be utilizing the oxygen in the stream, and at any level the dissolved oxygen concentration in the stream should not fall below the critical concentration. For example, 2 milligram per liter is the dissolved oxygen concentration required for aquatic life, and if you are bothered about very sensitive organisms, the dissolved oxygen concentration should not fall below 4 milligrams per liter. So, these things we have explained we have seen in detail last class, and we have seen that though the oxygen depletion is taking place in the river, there are other mechanisms by which oxygen is getting added to the stream. For example, the river water is in contact with the atmosphere, so definitely oxygen from the atmosphere will be getting dissolved into the stream. So, definitely it will be increasing the dissolved oxygen content of the stream. And another mechanism by which oxygen is entering in the stream is by algal photosynthesis. So, that also contributes significant amount of oxygen, but if it is a fast flowing river, then algal growth will be very negligible, because in turbulent condition algal growth is very less. So, in such cases the oxygen replenishment is because of the re-aeration from the atmosphere. So, if you want to see what is the oxygen profile in a stream or what is the quality of the stream with respect to the pollution or the effluent addition, okay, we can use dissolved oxygen model. Okay, we have today we will explain or we will see in detail this dissolved oxygen model. So, this dissolved oxygen model was developed by Street and Phillips in 1925. Okay, this model is used to predict the changes in DO deficit as a function of B-body exertion and stream aeration. So, this dissolved oxygen model is not taking into account the photosynthesis, because as I have already mentioned, in the streams because of the high turbulence algal growth will be negligible. So, this one we have seen last class also, the rate of oxygen removal or dy by dt is proportional to the concentration of organic matter present in the system, and we know that as the oxygen consumption increases, what will happen to the concentration of the pollutant? It will be decreasing with respect to time. So, that is why this negative sign is coming, and rate of DO disappearance is equal to rate of B-body exertion, because B-body is nothing but biochemical oxygen demand. So, as the BOD exertion increases, the rate of DO disappearance also will increase. So, that is what is written here, dy by dt, where y is the BOD exertion. So, rate of change of BOD exertion is proportional to the rate of change of DO disappearance, dd by dt. So, BOD exertion we have seen in detail when we were discussing about the water or wastewater characteristics. So, BOD exerted is nothing but whatever is the difference between the ultimate BOD, what was the initial organic matter concentration present and what is the organic matter concentration present at time t. So, if you take the difference, so that is nothing but the BOD exertion. That means this much amount of organic matter is being utilized by the microorganism and correspondingly that much of oxygen is utilized. Here L naught is the ultimate BOD and ultimate BOD is a fixed value and LT is the BOD or the organic matter left over at any time t. Or we can write like this, dy by dt, the rate of BOD exertion with respect to time, or rate of BOD exertion dy by dt is equal to minus dLt by dt, because we know that L naught is a constant. So, if you take the derivative of that one, it will be 0. So, dy by dt will become minus dLt by dt, and this dLt by dt we can replace by minus k into LT, because we have seen that the BOD exertion is a first order equation. So, the rate of change of concentration of organic matter is proportional to the concentration of organic matter present in the system, or in other ways we can tell that the rate of DO depletion dd by dt is nothing but k into LT, or this dd by dt we can replace by another term RD is equal to k1 into LT, and where RD is rate of change of oxygen deficit. Okay. So, I will explain once again. So, y is the BOD exerted, that is the difference between ultimate BOD and the organic matter concentration whatever is left over, or the rate of BOD exertion dy by dt is proportional to the concentration of organic matter left over in the system, or that we can write it as minus d by dLt by dt, and dLt by dt is equal to minus kLt, because we are assuming that the BOD exertion is a first order reaction, and this one we can, this dy by dt is nothing but minus dd by dt. So, we can write like this, dd by dt is equal to k into LT, or this dd by dt term we can replace by RD, where RD is rate of change of oxygen deficit, that is equal to k1 into LT. That means it is equal to a constant into whatever is the organic matter left over in the system. Now, we will see how can we find out the rate of oxygen addition. The reaeration is also assumed as a first order reaction. So, RR, the rate of reaeration is equal to K2 into D. RR is rate at which oxygen get dissolved from the atmosphere, and K2 is the reaeration rate constant, and K2 value is not a constant, it is affected by stream turbulence, surface area, water depth and temperature. If the stream turbulence is high, definitely this K2 value will be very high. The reason is when the oxygen has to dissolve in the stream, if the turbulence is there, then the mass transfer will be much easier. So, stream turbulence increases the K2 value, and if you have more surface area, so more contact surface will be available. So, definitely it will be increasing the K2 value, and if the water depth is high, so definitely the K2 value will be decreasing if you take per unit volume, because the surface available for the reaeration or oxygen transfer is less, and temperature, as the temperature increases, the dissolved oxygen concentration will be decreasing, because the solubility decreases with increasing temperature. So, at low temperature the solubility will be high, and high temperature the solubility will be less. So, these are the parameters what affect K2. So, whenever we find out the K2 value, it should be considering all these factors, or we have to apply proper correction for these changes. oxygen concentration is varying because of deoxygenation and reaeration. So if you want to find out the oxygen concentration in the river, okay, it will be a function of this reoxygenation and reoxygenation. So if you combine these two curves, the resultant curve whatever we are getting, it is known as oxygen sag curve. Oxygen sag curve is nothing but the summation of reaeration curve and the deaeration curve of the stream, okay, or in other ways the oxygen sag curve, okay, we are calculating the oxygen deficit, it is a function of oxygen utilization and reaeration, okay, or we can write in other ways dd by dt is equal to Rd, this is the reaeration rate and deaeration rate and this is the reaeration rate, or we can write like this K1 into Lt because this will be increasing the deficit and K2 into D, this is minus because it will reduce the deficit because if more and more oxygen get into the system, the deficit will be decreasing. So that is why we are writing like this dd by dt is equal to Rd, rate of deoxygenation plus rate of reaeration, that is equal to K1 into Lt minus K2 into D. So if you plot the curves separately, okay, we will get like this. So this is the, you see this curve, this is the cumulative oxygen depletion, okay, with a slope of Rd. So what is happening here? Here we are discharging some wastewater. So with respect to time, what will happen? Whatever is the organic matter present in the wastewater will be utilized by the microorganism. So with respect to time, the oxygen concentration will be decreasing. So we are taking the cumulative oxygen depletion. So you will be getting a curve something like this and finally it will be becoming asymptotic or almost nil. And the same time what is happening? The oxygen will be entering into the system because of the reaeration. So this is the cumulative oxygen addition to the system and the slope of the line is RR at any point. If it, and this line the slope is RD. So if you combine these two curves, what will happen? You will be getting a curve something like this. Okay, this will give you the dissolved oxygen concentration in the system. And here the x-axis represent time in days, or it can be the distance in the stream, and here you will be getting the dissolved oxygen. And here you can see that in the oxygen sag curve, this is the maximum dip available. This one, this is known as critical deficit and this is known as the critical concentration, and the time corresponding to that one is the critical time. So the critical time or critical deficit will not be occurring immediately after the waste discharge. It will take some time to occur the critical deficit. Okay, so we can find out the critical time or the distance at which the critical deficit will be occurring, and this information can be used for the management of effluent discharge. So this is the use of this dissolved oxygen model. We will be able to predict the critical deficit and the location where it is occurring and what is the corresponding dissolved oxygen concentration. And this line shows the saturation oxygen concentration. That means at a particular temperature, this is the maximum dissolved oxygen concentration the stream can have. So that is Cs. So now we will see the derivation of the dissolved oxygen model. So we know that Lt at any time, that means the leftover organic matter is equal to L naught into e raised to minus K1 into T, where K1 is the BOD exertion rate, or dd by dt we have seen earlier, dd by dt is nothing but K1 into Lt minus K2d. So this one we can write like this, dd by dt plus K2d, because that time is coming this side, is equal to K1 into L naught into e raised to minus K1t, because that is equal to K1 into Lt. Lt we are substituting by this value L naught into e raised to minus K1 into t. So this equation is in this form, dy by dx plus p into y is equal to q, where p and q are functions of x. So we can integrate this using this approach. This is the standard format, e raised to integral k to dt is equal to e raised to k to t. So how can we integrate this equation? So what we are doing is we are multiplying all the terms by e raised to k2 t. So the equation will become e raised to k2 t into dd by dt plus k2 into d into the same term e raised to k2 t is equal to k1 L naught into e raised to minus k1 t multiplied by e raised to k2 t, then we will be getting k2 minus k1 t. So this term if you see e raised to k2 t into dd by dt plus k2 d into e raised to k2 t is nothing but d by dt of d into e raised to k2 t. So we can write like this: integral d of d raised to e raised to k2 t is equal to k1 L naught into integral e raised to k2 minus k1 t into dt. So we are integrating this one because we got it in this standard format. So if you integrate this term, you will be getting d into e raised to k2 t is equal to k1 L naught by k2 minus k1 into e raised to k2 minus k1 into t plus c. This is the constant of integration. And how can we find out the constant of integration? We know that at t is equal to 0, d is equal to d naught, that is the initial deficit. So d naught is equal to k1 L naught minus k2 minus k1 plus c. Okay, you substitute. Okay, here t is equal to 0, then we will be getting this term d naught is equal to k1 L naught by k2 minus k1 plus c, or c is equal to d naught minus k1 L naught by k2 minus k1, or and we can substitute this c value in the earlier equation, this equation. So we will be finally getting d into e raised to k2 t is equal to k1 L naught by k2 minus k1 into e raised to k2 minus k1 into t plus d naught minus k1 L naught by k2 minus k1, where k1 is the deoxygenation constant and k2 is the reaeration constant and L naught is the ultimate BOD, d naught is the initial deficit. Okay, so we know all these terms. Okay, and from this one we can find out what is d. So you divide this expression with e raised to k2 t. So you will be getting finally the deficit at any time t equal to k1 L naught by k2 minus k1 into e raised to minus k1 t minus e raised to minus k2 t plus d naught into e raised to minus k2 t. So in the stream, if you substitute any t value, okay, we can get what is the oxygen deficit. So we can plot the dissolved oxygen or oxygen sac curve for the stream. Okay, so this t is nothing but x by u, where x is the distance along the stream and u is the velocity. So from this expression we can make the oxygen sac curve. But for the management purposes, this oxygen sac curve itself will not be enough, because we are interested to find out what is the minimum dissolved oxygen concentration available and what is the maximum deficit and what distance it is occurring. That is the most important things. So how can we find out those informations from this expression? Okay, so that is what I have written here. The most important point in the oxygen sac curve are the point of lowest DO, critical deficit DC and critical time TC, because at any point the lowest DO should not be below the specified limit, either 4 milligram per liter or 5 milligram per liter, depending upon the class of the stream or depending upon the use of the river water. And we know that at critical deficit, so at critical deficit you can see that the slope is 0 or rate of change of deficit is 0. So we can use that information for finding out what is the DC and corresponding TC. So that is what I have written here. Rate of change of deficit is 0 at critical deficit period. So we can write the expression like this: 0, this is nothing but dd by dt plus k2 into d. Okay, so we know that the deficit at that time is DC, the critical deficit, that is equal to k1 into L naught into e raised to minus k1 into t, and here the t is corresponding to the critical time. So we are replacing the t by tc. So our original equation will become 0 plus k2 dc is equal to k1 into L naught into e raised to minus k1 tc, or K2 dc is equal to K1 L naught into e raised to minus K1 tc. So we can find out what is the dc value. So dc is equal to K1 by K2 into L naught into e raised to minus K1 tc. So if you know tc value, then we can find out what is the deficit dc at that point. So how can we find out the tc value? So because unless you know the tc value, it will be difficult to get the dc value. So in order to find out the tc value, what we have to do is differentiate the equation for d with respect to t and equate it to 0. So we know what is the expression for d, okay, and we know that at the critical deficit, the rate of change of deficit is equal to 0. That is why we are differentiating the equation for d with respect to t and equating it to 0. So this is the expression for d, K1 L naught by K2 minus K1 into minus K1 into e raised to minus K1 tc plus K2 into e raised to minus K2 tc minus K2 into d naught into e raised to minus K2 tc. So we are differentiating it and putting it, equating it to 0. So you will be getting tc is equal to 1 by K2 minus K1 into ln K2 by K1 into 1 minus d naught into K2 minus K1 by K1 L naught, or the time is can be calculated based upon K1 value, K2 value, d naught value and L naught value. All these values are known to us, so we can find out what is the Tc or the critical time at which the minimum dissolved oxygen concentration can occur in the stream. So once you know the critical time, okay, we can substitute this Tc value here and we can find out what is the Dc value or the critical deficit, and we can also find out what is the concentration corresponding to that one, because we know what is the critical deficit and we know what is the saturation concentration. So Cc or the critical concentration is nothing but Cs minus Dc. So by using this dissolved oxygen model, okay, we can find out what is the maximum organic load we can discharge into a stream, so that the dissolved oxygen concentration of the stream will not be going below the specified minimum value. Okay. So that is the most important use of this dissolved oxygen model, but there are certain disadvantages of this Streeter-Phillips equation, because they have considered only one discharge point for the waste, but we know that if you take a stream, it will be having many point sources of wastewater coming to the system. So what will happen? Okay, we have to make the oxygen sac curve for each discharge point and we have to superimpose that one. Then only we will be getting the actual oxygen sac curve. And another one is, okay, this one has taken, this dissolved oxygen model has not taken care of the algal respiration or the reaeration due to photosynthesis. But if the river velocity is very less, then photosynthesis will contribute significantly to the dissolved oxygen concentration. So that is another problem. And we know that apart from the organic matter, other constituents like organic nitrogen, organic phosphorus, etc. will be exerting some amount of oxygen demand, because if organic nitrogen in the form of ammonia is present, we have seen that 1 mole of ammonia oxidation require around 4.52 moles of oxygen. That means ammonia has to convert it to nitrite and nitrate. So it requires lot of oxygen. So these things are not taken into account in the Streeter-Phillips equation, or this is the simplest model available for predicting the dissolved oxygen profile of a stream. So if you want to get the actual dissolved oxygen profile, we have to take into account all these other reactions and other parameters like photosynthesis, organic nitrogen, organic phosphorus and algal decay, etc. So nowadays many commercial packages are available which takes care of all these aspects, and we can get the dissolved oxygen profile of the stream. Now we will see how to discharge the wastewater to the streams. Okay. So either we can put the discharge point like this, that means it is below the water level in high water level period and it is above the water level during summer or low water level period. Okay, so this is the example. So this is the discharge pipeline from wastewater treatment plant, and here we usually give a concrete splash pad to avoid the erosion, and at low flow periods because of air entrainment, foaming often occurs where simple discharge is used. Okay, so that is another drawback of this system, because in summer or in low water level the water is falling from such a height. So what will happen, because of the turbulence and entrainment, air entrainment, here foaming can take place. So if you want to avoid the foaming, it is always advisable to put the pipeline in the bottommost portion of the stream. Okay, that is what is shown here. Discharge pipeline from the treatment plant, submerging of the discharge pipe below the low water mark will eliminate foaming problems. So according to the requirement, we can put either this way or this way. Okay, and whenever we discharge the treated effluent, okay, we have to use proper diffusers, and to avoid foam, submerge the discharge pipe. And another water body usually the wastewater is being disposed is estuaries, and estuaries is the zone where the river meets the sea, and in estuaries because of the tidal action increased dispersion will take place. Because of the dispersion there will be the dilution of the wastewater or dilution of the pollutant will be taking place. So we can see that, okay, this is the concentration and distance in the downstream. Okay, this is the plug flow model. If it is a completely plug flow, you will be getting this type of concentration, but because of the diffusion what will happen, this will be getting diluted like this, and as the distance increases, okay, the concentration will be coming like this and coming like this. So it will be almost uniformly getting mixed after a particular distance. And another water body where the disposal is possible is ocean. So in ocean disposal usually submarine outfalls are used. So this is the wastewater coming from a treatment plant, and this is the outfall diffuser, and this is the mean low water level. And whenever we put the ocean outfalls, it is always advisable to keep around 500 meters from the beach. This is a typical cross section of a ocean outfall, and we will see how the wastewater mixing is taking place once we discharge the wastewater either in the ocean or in the estuary. The two phenomena which are responsible is, one is advection and another one is diffusion. There is certain amount of biodegradation also takes place in these regions. Okay. So whenever we design the outfalls, okay, the receiving water standards on dissolved oxygen, bacteria, floatable material, nutrients and toxicants should be satisfied, because at any case, because all these water bodies will be having lot of aquatic organisms. So the dissolved oxygen concentration should not fall below the specified minimum dissolved oxygen concentration. And another thing is pathogenic bacteria. If the pathogenic bacterial concentration are more, okay, if the people are using or the aquatic organism, it will be getting affected by the microorganisms. So the effluent discharge standard should be met even when we discharge the effluent to the existing huge water bodies. And floatable material also, if floatable materials are there in the treated effluent, okay, it will be making obscene scenes. Okay, so it's always advisable to remove all the floatable material. And if the nutrient concentration is high, what will happen? Algal blooms will be taking place. That means the essential nutrients like nitrogen and phosphorus, if it is more than the minimum requirement, so algal growth will be very high, and that will be affecting the water quality. And the effluent whatever is coming to these water bodies should not contain any toxicants, or the toxicants concentration should be within the specified limit, otherwise it will be affecting the users. So each and every water body will be having a specified standard. This standard is made based upon the beneficiary use or the use of that water, because if the stream in the downstream end is used for the drinking water purpose, definitely the standard will be more and more stringent, and if it is only using for the navigational purpose, the standard will be little more relaxed. Okay. So, depending upon the downstream use of the water body, okay, the receiving water standards have been put up, and we have to satisfy that standard after this advection, diffusion and biodegradation. Whatever is ultimate concentration coming, it should be within the permissible limit. And how can we estimate the initial dilution whenever we discharge it into the ocean? Okay. It is depending upon the climatic conditions. So, what will happen when we discharge the wastewater into the ocean? Under the wastewater always will be warmer and lighter compared to the sea water. So, what will happen, even though your ocean disposal point is much below the low water level, the wastewater eventually reaches the surface, because as it comes out of the disposal point, what will happen, some velocity will be there. So, with that velocity or with the momentum, it will be rising, and compared to the surrounding water in the ocean, this water temperature will be higher and the density will be lighter. So, what will happen, this water will be having, the wastewater will be having a tendency to push apart the ocean water and come up. So, it will be forming a layer over the ocean water. So, usually this occurs in summer time, because in summer time most of the time the wastewater temperature is much more than the sea water or the ocean water temperature. And during winter, what will happen, the wastewater temperature will be less compared to the sea water, but the density is also less. So, it will not be able to come up to the top of the ocean. So, what will happen, it will be getting submerged in between the ocean water. So, during winter time, most of the time you will be getting a submerged plume, whereas in winter time the sea water will be coming into the top of the ocean and forming a floating layer. So, it is always advisable to avoid the floating layer, because if the water is floating on the surface of the sea water, what will happen during tides and because of the waves, all this pollutant will be coming to the beach, and that will be adversely affecting the people who is going to the beach or using the beach for swimming purpose. Now, we will see, okay, we have seen how can we dispose the effluent coming from the treatment plants, but not only the water bodies can be used for that purpose, sometimes we can go for land disposal also, because in the land if you put the wastewater, okay, it will be acting as a water source for the land. Moreover, the wastewater will be having lot of organic matter, nutrients, etc. present in the system. So, what will happen, these nutrients can be utilized by the plants and a higher degree of treatment can be achieved. So, this itself is known as land treatment systems. So, if you want to see what is this land treatment systems or phytoremediation, here use of plants, the soil surface and the soil matrix for wastewater treatment. So, that is what is known as land treatment systems. So, land treatment of wastewater can be done either using irrigation or by rapid infiltration or by overland flow. So, these are the schematic of each and every process. So, this is the irrigation. So, what is happening? So, this is your land. So, these are the plants. So, you are sprinkling the water on the surface either by using sprinklers or by surface application. You can supply the water here. So, what will happen? The water will be percolating, okay, and this is the root zone. So, in the root zone, the soil will be loose and lot of microorganisms will be there. So, those microorganisms will be taking care of the organic matter and other nutrients whatever is present in the system, and it will be getting removed, and the leftover water whichever is relatively clean, it will be coming through the soil or it will be percolating, and finally it will be reaching the groundwater. And this is the other thing, that is rapid infiltration. So, what we are doing, we make a trench and here the water, the wastewater or the effluent whatever is coming from the treatment plant is applied. So infiltration is taking place and percolation through the unsaturated zone. So this was your existing water table. So because of this infiltration, recharge is taking place. We can see that the water table is increasing like this. And this is the example of overland flow. So what is happening? This is the grass and the vegetative litter. So they will be utilizing the organic matter and the nutrients whatever is present here. So the water will be getting relatively clean, and finally it will be coming to the existing water bodies, which is relatively cleaner than whatever we have applied to the land. So these are the different methods of land treatment, and there are different aspects. Okay, if you want to go for irrigation, we can apply using sprinklers or surface irrigation, and rapid infiltration usually surface application is used. Overland flow usually sprinklers or surface application can be used, and another treatment method is wetland application. Here also sprinklers or surface application can be used, and subsurface application, subsurface piping is used. Okay, so these are the different methods used for the water treatment using land, and nowadays the wetland application and subsurface applications are gaining more and more attention. And if you want to go for this land treatment, the wastewater whatever is coming from the treatment plant should be meeting certain conditions. The BOD should be less than at least 15 milligrams per liter, and suspended solids, if you go for overland flow should be less than 20, and if you are going for irrigation, it should be less than 5 milligrams per liter, and ammonia and nitrogen, it should be less than 2 milligrams per liter, 2 milligrams per liter at any case, and irrigation and all those things. Okay, in all the cases ammonia nitrogen should be less than 2 milligrams per liter, and total nitrogen should be less than 5 to 8 milligrams per liter, and total phosphorus should be less than 0.3 milligrams per liter in case of irrigation, and for rapid infiltration should be less than 5 milligrams per liter, and overland flow it should be less than 6 milligram per liter. The reason is, if you put the wastewater with high pollutant concentration, what will happen? The land will not be able to take care of the pollutants properly. So some of the pollutant will be left over after the land treatment, and it will be percolating, and it will be going and meeting the groundwater. So whatever is the existing groundwater, that also will be getting contaminated. And in overland flow, what will happen? The wastewater will be flowing over the land, and the plants are supposed to take care of all the leftover pollutants in the water. But if the pollutant load is very high, the plants whatever is present in the system will not be able to take care of all the pollutants. So the leftover pollutants will be going and meeting the existing water bodies along with the water. So that will contaminate the groundwater and the surface water sources. So we will see each one in detail. For example, irrigation. Irrigation is the application of effluent to the land for treatment. So the purposes are to meet the plant needs, and it will also give physical, chemical and biological treatment to the effluent, and application can be done by sprinkling or by surface techniques. We have already seen this one. And the advantages of this irrigation is avoidance of surface discharge of nutrients, because if you just discharge it to the existing water bodies, lot of nutrients will be going to the existing water bodies, and that will be increasing the algal growth. And it also give economic return, because the irrigation water quantity, the pure water can be reduced, and whatever is the nutrient present in the wastewater or the treated effluent can be used by the plants. So the fertilizer requirements can be reduced considerably. And the next one is water conservation. Okay, we are not wasting the water. And preservation and enlargement of green belts. Okay, when we have lot of water available with high nutrient content, naturally the preservation and enlargement of green belts can happen. And whenever we apply the effluent for irrigation, the loading rate is important. the place where water scarcity is there, we can go for 2.5 to 7.5 centimeter per week, and water availability is not a problem, then we can go for maximum hydraulic loading of 6 to 10 centimeters per week. So, this 2.5 to 7.5 centimeter where the water scarcity is there and water availability is not a problem, you can go for a higher loading. And the major objectives are groundwater recharge and natural treatment, followed by pump withdrawal or under drains for recovery. So, after the irrigation, okay, if you can place the drainage, proper drainage system, we can collect the water for reuse, and natural treatment with renovated water moving vertically and laterally in the soil and recharge a surface water source, that is also possible because of this method. Now we will see this overland flow. What is happening in overland flow? Wastewater is applied over the upper reaches of the sloped terrace, allowed to flow across the vegetated surface to runoff collection ditches. So, it can be treated as a secondary treatment. Okay. For example, some degree of nitrification will be taking place if the BOD of the wastewater is low, and advanced wastewater treatment can also take place. The reason is the soil will be acting as an adsorbent, so it will be taking care of most of the other organic matter present in the system. And what are the fundamental considerations when we go for land treatment? The wastewater characteristics and the treatment mechanisms are very, very important. For example, if the organic matter content, this organic matter whatever is present in the effluent, it will be utilized by the microorganisms whatever is present in the soil. So, if the organic matter content is less, it is fine, the soil microorganisms will be able to utilize the organic matter. But if the organic loading is high, what will happen? The oxygen available will be limited and the microorganism will try to utilize the organic matter. So, anaerobic condition will prevail in the soil. So, as a result what will happen? Lot of odorous gases will be generated and the entire place will become non-usable. Okay. And similarly, if the nitrogen concentration is high, okay, if it is within the permissible limit, it will be acting as a nutrient for the plant. But if the nitrogen concentration is very, very high, what will happen? Okay, the ammonia nitrogen has to be converted to nitrate. But if sufficient oxygen is not there, nitrification will not be proper. Similarly, phosphorus also. And another one is the presence of exchangeable cations. If large quantity of these exchangeable cations are present in the system, that will be changing the permeability of the soils, or the soil characteristics will be changing. So, this one we can measure in terms of SAR. This is nothing but sodium absorption ratio. This can be calculated using this formula, Na divided by root of Ca plus Mg by 2. All the concentrations are expressed in terms of milliequivalents per liter. If SAR is more than 9, it is not advisable, and we should be careful about trace elements like heavy metals and all. If it is present in the soil, we cannot destruct them. So, what will happen? If heavy metals are present, the root zone will be absorbing those heavy metals and it will be getting accumulated in the plant. So, when we consume any part of the plant, what will happen? It will be coming to us. Similarly, the microorganism, many pathogenic microorganisms may be present in the effluent whatever is coming from the treatment plants, and if we use that water for the irrigation purpose and we use the vegetable in the raw form, so what will happen? These microorganisms may be present in the raw vegetables and it will be harming the health of the people whoever is using that vegetable. And another important thing is the vegetation, the type of crops or the type of plants present in the system, because if the plant is able to take care of lot of nitrogen, phosphorus, and if it requires lot of water, then that type of a plant is, or the vegetation is more preferable for land treatment. And another important aspect we have to consider is the public health, because the treated water, as I have already mentioned, it will be containing lot of bacteriological agents. This can cause diseases, and if the land treatment is not proper, what will happen? The groundwater quality will be getting affected, because partially treated water will be penetrating percolating to the groundwater, and entire groundwater quality will be getting affected. And another one is the crop quality. Okay, it also will be getting affected. Okay, and when we go for these irrigation systems, okay, what are the design objectives we have to consider? The main objective is the treatment of applied water. How much treatment we can provide, because that is very, very important. And another one is what is the economic return from the use of water. The third one is what is the extent of water conservation we are doing, and what is the extent of preservation and enlargement of the green belt possible. And for the objectives of treatment, the hydraulic loading is very, very important, and it is limited to the infiltration capacity of the soil. Okay, if the hydraulic loading is more than infiltration capacity, the water stagnation will be taking place, and under trains can increase the allowable loads, because what will happen, water is percolating through the soil. If we can collect it and pump it up, then the loading can be increased. Use of grasses improve the nitrogen uptake capacity. And for economic returns, a hydraulic loading of 2 to 8 centimeter per week is recommended, and off-season storage to allow irrigation of the maximum area in summer is essential, because in the winter the water consumption will be less. So we may have to store the effluent for the irrigation purpose in summer. And what all are the pre-application treatment required? It is based on the public health regulations or guidelines. So based upon the regulations, we have to achieve the treatment, and factors need to be considered for this irrigation are type of crop ground and intended use of the crop, degree of contact by the public with the effluent, and method of application. All these things are very, very important. So if you are going for food crop, so naturally, okay, we have to be very, very careful, because the bacteriological agents whatever is present in the wastewater can affect the crop quality, and that invariably affect the health of the public. And the degree of contact by the public, okay, with the effluent. Okay, if the plant needs continuous attention, so the people will be going into the land, and that will also cause diseases and all. And other one is the method of application. And again the climate and storage, that is also important. Wastewater application is restricted only to the growing season, because then only the plants can utilize the nutrients. And storage of 1 to 3 months is moderate in moderate climates, and 4 to 7 months in cold climates are required. And loading rate we have already seen, and hydraulic loading rate should be such that the design precipitation plus wastewater applied should be equal to the evapotranspiration plus percolation. This is very, very important. If you add more water, then what will happen? Water logging will be taking place. And this is the nitrogen loading, because nitrogen loading will be based upon the nitrogen uptake capacity of the plants. So N equal to 0.1 into Cl, where N is the annual nitrogen loading kilogram per hectare year, and C is the total nitrogen concentration in the effluent, that is given in milligrams per liter, and L is the annual liquid loading centimeters per year. And similarly phosphorus also we can calculate what is the extent of phosphorus we can give, and this is the organic loading. The recommended organic loading is 11.2 to 28 kilogram per hectare per day. And land requirement based upon the organic loading, we can find out the field area required, that is equal to 3.65 Q by L, where Q is flow rate in meter cube per day, and L is the annual liquid loading centimeters per year, and field area we will be getting in terms of hectares. And the important aspects are nitrogen removal capacity. Now, whenever we take the crop, the important aspects are nitrogen removal capability and water needs tolerance. And other systems are wetlands and aquaculture. Now we will see the direct and indirect reuse of wastewater. Nowadays this reuse of water is gaining much more attention, but we all know that complete reuse of water is impossible in most of the cases. The reuse potential depends upon the availability and cost of fresh water, transportation and treatment cost, water quality standards, and reclamation potential of wastewater. So why we have to go for the reuse? The need is to meet the increasing water demand, because we know that the water is not available plenty in all the locations. So we have to meet the increasing water demand. The second one is to protect the water bodies, because we know that the effluent, whatever is coming from the treatment plant, will be having some amount of pollutant. But if we can treat that one and reuse it, the pollutant whatever is going to the existing water body will be limited. So we can protect the water bodies. These are the two major objectives. So what are the different ways of water reuse? The first reuse was sewage farming, whatever we have seen till now. And when we talk about the water reuse, what are the public health and environmental issues of water reuse? First one is the constituents, because there will be conventional pollutants, non-conventional pollutants and emerging pollutants. Conventional pollutants, organic matter, nutrients and microbes, we know that the land can take care of this one. And non-conventional means volatile organic compounds, surfactants, refractory organics, etc. To a certain amount these are biodegradable, but some are really refractory organics. And emerging compounds, this creates maximum problem. Those include non-prescription drugs, home care products, antibiotics, industrial and household products, steroids, etc. So most of the cases these compounds will be coming out after the treatment also. So when we go for the reuse, we should be aware of these compounds and what is the adverse effect of these compounds. And another one is public health issues, because of the emerging compounds and acute and chronic health effects of these emerging compounds. And this acute and chronic health effects depends upon the concentration and the exposure pathways. And third one is environmental issues, because nobody knows what is the long term effects of these emerging compounds, because most of them are very new to the system. So these are the concerns. And so if you want to go for this one, okay, we have to go for a risk assessment. So what type of a risk assessment we can do for the water reuse? One is the hazard identification. Whenever we want to go for a water reuse, we have to find out what are the hazards involved in that process. And second one is exposure assessment. So if you reuse the water, what are the possible exposure because of the reuse? And second one is, third one is dose response assessment. We know what are the hazards and what is the potential exposure. So if you know these things, and we can find out what is the dose response of the pollutant, because if this much of concentration enters in the body, so what is the effect in the body, then we can find out what is the risk, and once you know the risk, we can go for the risk management. So this is essential whenever we go for a water reuse project. The risk assessment is very essential. Now we will see what are the different ways we can reuse the water. One is municipal, another one is industrial, third one is agricultural reuse, fourth one is recreational, and fifth one is groundwater recharge. In municipal reuse, okay, the dilution in natural waters to the possible extent is taking place, and afterwards the same water body is used for the drinking water purpose. So we give the treatments like coagulation, filtration, disinfection, adsorption, and most of the time this is practiced in emergency base, and desalination and demineralization is also need to be done to remove all the compounds or all the molecules present in the water, and this is technologically feasible, but the cost involved is very high. And industrial reuse, the greatest user of the water, the largest demand in industry is for cooling water. So treated wastewater can be used for cooling purpose, but the problems associated with this one are the scale formation, metallic corrosion, biological growth, and fouling. The treatment required after the conventional secondary treatment are denitrification, lime soda softening, filtration and disinfection. Even after this treatment, sometimes these problems are occurring in the cooling water circulation pumps. In agriculture reuse we have seen in detail. Okay. So the quality of effluent is very important, and the amount of effluent used is also important, and we have to see the health regulations concerning the use of treated and untreated wastewater on crops, and vegetables consumed in raw state cannot be irrigated using wastewater because of the potential health hazard. And now coming to the recreational reuse, okay, we can use the water for golf course and park watering, ponds for boating and recreation, maintenance of fish or wildlife ponds. And we can also use the effluent for groundwater recharging. The treated water for groundwater recharge increase the groundwater table, prevent the saltwater intrusion, and recharge oil bearing strata to increase the oil yield. But whenever we go for the groundwater recharge, we have to see that all the pollutants, whatever is of important in terms of health, is removed from the system, otherwise entire groundwater will be getting polluted because of the pollutants present in the system. So that is why nowadays the land treatment is not advocated much, because in the land treatment earlier what was assumed is in the water zone where the root or the root zone where the root of the plants are there, lot of microbial activities will be there. So that region will be able to take care of all the pollutants whatever is present in the system. But the traces studies shown that the water will not be distributed evenly throughout the soil surface. It will be taking some particular paths and coming to the groundwater. So the groundwater will be getting polluted. So if you want to go for the ultimate water reuse, what we have to do is we have to plan in the following way. First we have to assess the wastewater treatment and disposal need, then an assessment of water supply and demand is required, and assessment of water supply benefits based on water reuse potential is essential. Then the analysis of reclaimed water market and environmental and economic analysis, implementation plan and financial analysis, and public information program. So all these things are essential before going for any wastewater reuse program. Though the technologies are available or many technologies are feasible, even now the wastewater reuse, especially for drinking water or domestic purpose, is not gaining much attention, okay, because the cost involved is very high and public awareness is very important for this purpose. So now we will conclude whatever we have seen today. So we were discussing about dissolved oxygen model. So we have seen that using that model we can get the dissolved oxygen profile of the stream, and we will be able to find out what is the maximum deficit and the location where it is occurring. So based upon this we can manage the wastewater discharge into the stream. Then we have seen other disposal points like estuaries and oceans. Then another method of handling the effluent whatever is coming from the treatment plant is land treatment. But nowadays the land treatment is not advocated because of the partial treatment that is occurring in the system, because many non-conventional pollutants and emerging pollutants are present in the wastewater. Most of the time the land is not able to take care of that one, and we can go for water reuse based upon the economy and the requirement of the reuse water.